Hello there, everybody. Good morning for some, I guess good afternoon for most of you. Welcome to the webinar that we're hosting today here at Fluidit. My name is James Armour. I'm the host from the Fluidit side, and I'm here with a stellar lineup of various consultancies and utilities from across the, northern region, kind of North Sea and Scandinavia, or I should say Nordics. Here to talk all about district heating and district energy networks. And what I thought would be a nice use of our time over the next minute or so, just as people are rolling in, would be for you participants to give us a little inkling as to where you're coming from today. Maybe you could just pop in the chat your name, organization, the country, and we could get a better understanding of who's actually joining us today, and what you all represent and where you're coming from. And you'll notice that this is recorded today, so you're going to be able to watch this recording after the webinar is over. And please ask questions as we go. You can just put them in the chat, and I'll run through the agenda in a minute, but there'll be opportunities for them to be addressed as we kind of go through our speakers. And great, I can start to see people are leaving some comments there as to where they're coming from. So thank you all very much for that. And I think I can otherwise just get started on at least introducing the speakers that we've got here today. We have, as you can see from the screen, and also a couple of videos on, we've got Gabriel Gallagher from Sustainable Energy, so he's based in the UK. Managing Director at the UK-based consultancy firm there. We've got Dr. Egil Thorbergsson from Veitur, so he's their research and development lead, and I saw a smile from him there, so I clearly got the Icelandic name down to a T. And we have Panu Kauniskallio from Fortum over in Finland. I hope I also got that name correct there. And he's working as a systems specialist, so modelling and network planning. And myself, I'm of course coming from Fluidit, and I think nice to jump right into a little bit of an agenda for the day. Of course, we don't have tons and tons of time, but really the plan was, once I've gotten past these introductions, that we would take a little look at each of these different cases. So starting with the UK, 10 minutes apiece, going into Iceland, and then finally Finland. And actually, as we're going, please ask questions as they come up, and between each speaker we could probably put in a minute or two to maybe discuss a little bit more about that specific region. But certainly at the end we'll have time for questions in the final remaining minutes there. And I'm also quickly just going to give you all a short introduction to Fluidit and who we are before I hand it over to our first speaker, because we are all working together in partnership. Fluidit is a hydraulic modeling company, so we create software for planning and optimizing hydraulic networks. So it's district energy, but it's also water networks, sewage networks, and stormwater networks. And the organization is based in Finland, and we're working in 21 different countries around the world today. And I will not go too much further into the Fluidit topic, as we don't have so much time today. So I'm actually just going to hand it straight on over to Gabriel and give him the floor for the next 10 minutes to tell us a lot more about what's going on in the UK district energy space. So please, Gabriel, the floor is yours.
Thank you, James. Don't seem to be able to share. Sorry, do you need to...
Yes, I could just make sure that that's also presentation on for yourself. Here we go.
Thank you.
And now it should be activated.
Great. So, give me a second while I adjust my screens again.
It's good for us.
Okay, great. Good afternoon, everyone. Gabriel Gallagher, and I've got 25 years experience in renewable heat and district heating, and I'm Managing Director of Sustainable Energy Limited. We're a team of engineers, consultants, designers specialised in district heating, and our projects take us through from feasibility, design, project development, and clients engineer. And we are a Fluidit user. So I'm going to give you a quick, brief introduction to a few of the heat networks we've been working on. So really the UK context, I guess, is that, district heating is viewed as a significant opportunity for decarbonising heat in UK. There are many local area heat networks operating in UK, but these are generally sort of smaller, built from communal housing schemes or some CHP-led schemes and some waste to energy schemes. But so the citywide low carbon heat network in UK are really at the sort of early stages of development. And how can those heat networks develop in UK cities? So really, this is a quick whistle-top tour of 3 examples and experiences of different approaches using different heat sources. So first project I'll pick on here is the sort of 3 megawatt water source heat pump, which is supplying some of the early Bristol city centre heat networks ahead of the growth and potential future strategic heat network. The second opportunity or project that we're working on here is the energy from waste heat offtake from a city incineration and power plant, and that's to bring a heat network spine into the city to initiate the heat network in Cardiff. And then on a sort of smaller scale, but interesting nevertheless, is sort of the approach of a new village built around 1,500 homes, community amenities, using mine water as the source for a heat pump. So first off, developing heat network from the centre, which is basically our Bristol example here. So way back, I guess, 10 years ago, we started looking at that sort of red area in the middle there, which is called Redcliffe. So the initial feasibility and design for the scheme at this stage, or at that time, heat networks in UK were really sort of focused on where is the the high intensity of heat and starting there. From 2015 through to 2018, all the further sort of areas of the city were developed, and feasibility studies put around that, with construction starting around sort of 2017, building out some of those the 3 networks in the centre, which we call them Old Market, Redcliffe, and Bedminster. So by 23, there's some 4.5 megawatts of low carbon sources, 3 megawatt heat pump, biomass boilers, and CHP, with a peak capacity around 12 megawatts currently. But that medium growth scenario, the mapping and the opportunities there is probably in excess of 100 megawatts, with some 1,000 bulk heat connections potentially added to that. So those networks are envisaged to build around maybe future heat pump sources within the city, air sources more from the harbour, and some wastewater sources. But once those areas have built out on their local low carbon sources, the demand is going to outstrip supply in what we could see at the moment. There's just not enough areas that we can generate enough heat in the centre of that city to supply the whole city. So that future demand must be come from outside the city, and really that's an area we're looking at the moment. There's obviously the blue line at the top, which is a connection to an industrial area with energy from waste plants and industrial waste heat available. But how are these different networks then connected together? Maybe a ring main, and this is just an area of ongoing investigations we're running and models we're running at the moment, and using the Fluidit software. Different sort of approach, I guess, to another city is the Cardiff Heat Network, and this is sort of the other way around. This is there's a existing energy from waste plant close to the city centre. There's a number of key existing buildings in the area, and this is where the heat network starts from the spine network, building through to key buildings, and with I guess the first phase just being 11 buildings, 11 key large buildings, but future phases then connecting in the proximity of that spine, that capacity, current offtake There's around 15 megawatt from the EFW plant, the energy from waste plant, with backup boilers in the vicinity. But as this network grows and the opportunities extend and go beyond the available sort of circa 15 megawatt at the moment, that original spine was sized around to sort of deliver capacity around sort of 25 megawatts, so future-proof there. And really it's then looking at what the future sources of heat could be to supply into this network. And fortunately, this has a number of water sources which are sort of available in the proximity of where the spine network is, and these are seen as the sort of future low carbon energy inputs into that network. So I guess a different way around than the previous project. And my last project is the heat network for a new build carbon village. So this is a greenfield site, and there's a development looking to build 1,500 homes, school and community facilities. The opportunity here is a nearby coal mine water treatment plant, and this has a resource around circa around 20 degrees C. And even though the feasibility set out that it's quite low or medium density housing and buildings in this area, what we were able to determine was the higher COP from that more warmer mine water source basically created a carbon and cost case for a small heat network supplied essentially from the mine water workings, and that was compared against the counterfactual, or the alternative, which was individual air source heat pumps. So this is a project that's sort of in final stages of procurement and shortly hopefully into construction, but just another example of different approaches to heat networks in the UK. So in summary, there's sort of three different approaches. That's building from the centre of the city on low carbon energy sources, gaining a capacity which then warrants and creates the economies to bring a much longer pipe from far outside the city, versus a low carbon and low cost source of heat fairly close to the city and actually starting from that point and building into the city, versus new build areas where the alternative are currently viewed with UK looking to sort of ban gas boilers from new houses. That the alternative is individual air source heat pumps, and when do heat networks then compete and offer a benefit against those cases. And that's just three examples of many more innovative heat networks that are under development by all sorts of organisations across the UK. And the implementation of low carbon heating has been proven. So there's a current 2050 target of 20% of heat to be supplied by heat networks in the UK. I mean, that's a much lower rate than I guess the following presentations and other Scandinavian cities will say. And I think we believe that also that it's a very low target, and the opportunity is far greater. But it leaves us, in UK, where it's a much earlier developed market. What is the opportunity? And the opportunity really is that we need to sort of plan and think big, start somewhere small, and grow those networks, and that's our UK experience. So thank you all. I'll pass back over to the team.
Superb, Gabriel. Thank you very much for that presentation. And
I guess questions at the end, isn't it? Is that right?
Questions at the end. Yeah. I was wondering, since we had a minute, if you would be able to, if I could chip in with a short question here, and it was really around kind of driving actors behind this, because I'm seeing such unique cases in different regions and unique sources and unique fashions of building out the heating network. And I'm curious, is it the councils, is it the utilities, is it the businesses? I mean, who's really driving this forward in most cases? How are you seeing the actual implementation?
Yeah, interesting question. I guess the three examples I've given were actually all probably pretty much driven by local authority. yeah, not on purpose, but yeah, now you asked the question. Yeah, they're pretty much local authority driven projects. Some with significant sort of local authority ownership. Some where they've, such as Bristol, where actually it was developed by the local authority, but then it was, a joint venture was created with an energy company to take that forward. Special purpose vehicles set up, and then in the case of the last one there, really more of a sort of, although the local authority was the driving force behind it, the sort of the commercialization of it would be more of a sort of concession basis, and without the local authority being involved. So yeah, three commercially different approaches, but the common thread being that local authority driver into those networks.
Superb. Well, thank you very much for the presentation, and I can then segue over to our next speaker, Egil, if you want to take the floor.
Sure. Thanks, Gabriel. It's a little bit interesting to come after you, since we here in Iceland have started building district heating networks in the 1930s, and also in the 1970, when the oil crisis hit, we implemented district heating network for the whole capital area. So I will share here my screen. So yeah, my company is Veitur, and I will go into a little bit more detail about the company later. We run a district heating network here in the capital area, where we see this picture of the capital area. So let's see. Yeah, so this is Iceland. We need heating throughout the year, both of course the winter and but also in the summertime. Then here is a figure of Veitur. So as I say, Veitur is owned by Reykjavík city, the municipality, and Akranes, a small city here in the west, and also Borgarnes, but most of it is owned by Reykjavík, the municipality. So we run the district heating network for the capital area. However, we also run it in a couple of small towns in the west part of Iceland, and also in the south part of Iceland. But I will focus mainly on the capital area today. So Veitur is has the district heating. We also have water utilities, wastewater utilities, and electric utilities. But yeah, we will focus today on the district heating network. Geothermal district heating, we of course we only have geothermal district heatings here at Veitur. It's very small amount of greenhouse gas emissions that comes just from the geothermal water in the power plants. And of course, it's very sustainable and very efficient and cost effective. I was going to, because this is a little bit different than usually you run district heating network, so I wanted to show a little bit just a very simplified diagrams of how geothermal system looks like. So we have a geothermal well. Most often we have a pump in the well that pumps up the hot water, but we have also a couple of wells that are artesian, so the water just flows from the wells. Most often the temperature is around 80 to 90 degrees. We, however, have some wells that are quite low temperature, 65 degrees Celsius, while we also have quite high temperature wells up to 140 degrees Celsius. This is a simplified diagram of an open system. That means we only have the water going into the houses, and we try to pump it at 80 degrees into the from our pump stations into the system and to our customers. We, however, have a couple of systems that we are running at much higher temperature, around 95 degrees Celsius. And since it's an open system, we just the customer gets the water, and it flows into the drain at the customer sites. So we don't have any return water. So this is called the open system. But we also have a semi-closed system. Because the temperature is over 80 degrees Celsius, what we do is we take a little bit of the return water back into our system, so then we have return pipes and mix the water. So maybe you have a well that has 90 degrees Celsius. We mix it with return water that has 30 degrees Celsius, and we pump into the houses 80 degrees Celsius. So this is a semi-closed system. And most of Reykjavik, for example, has this kind of a system, semi-closed system. So yeah, we don't we have both flowing into the houses and also return pipes in our system, and that we always have had this kind of a system. So we also have power plants that uses high temperature geothermal resources to produce both electricity and hot water. We then, for the power plants, we heat up groundwater from 4 degrees Celsius to, with heat exchangers, to around 85 degrees Celsius. And then it's a semi-closed system because we take small amount of return water and mix it so that we pump into the houses water around 80 degrees Celsius. But this is not geothermal water, this is groundwater, cold water that we have heated up. Then we have also system that's completely closed system. So then it's more like a usual system where we use the geothermal fluid to heat up a fluid that's in a closed system. So we have two systems like that in Hveragerði and Stykkishólmur. So this is how the houses for the wells look like here in Reykjavik. So for Reykjavik, the capital area, we have 4 geothermal resources. Laugarnes, which is in the downtown here in Reykjavik, has a temperature of 130 degrees Celsius. While Elliðaárdalur and Reykjahlíð and Reykir, the other systems, it's around 80 degrees Celsius, those systems. And the low temperature sources, they produce around 40% of the peak power. And the peak power for the capital area is around 1100 megawatts, the peak power demand. We also have 2 power plants, geothermal power plants. Nesjavöllur, which was started to build in 1990s and then was built in several stages to 2005. It produces around 120 megawatts of electricity and 350 megawatts of thermal for the hot water. And we get around 85 degrees from that power plant. Hellisheiði, which is much newer, they started building that in 2006 and can produce around 300 megawatts of electricity and 210 megawatts of thermal. We get around 84 degrees Celsius from them. So this is the capital area. So since we have low temperature resource and then we have heated up cold water from power plants, we cannot mix that water is not the same as water. So we can't mix the groundwater and the geothermal water. So in theory, we have 2 different district heating networks for the capital area. The red zones get the geothermal water, while the blue zones get power plant water. And just a little bit about the history and where we are going. So this is in the start 1970s, we got all of the water from the low temperature fields. Then in the 1990s, we got the power plant Nesjavellir in operation and could reduce the amount that we were taking from the low temperature fields, going into a more sustainable production from the low temperature fields. But we are going fast forward. The capital area is always increasing in size. We have large areas in development, and last 45 years, the increase in the average production was around 30 liters per second per year. That means in peak demand, it's around 70 liters per year, while the last 10 years, the average increase in the average production was around 50 liters per second per year, which is around 120 liters per in peak demand. So we are always looking for more resources and for the future demand. And here on the right, we can see our forecast, low forecast and high forecast. We have been looking at the population forecast and also just what are the capital area, the municipalities master plan in development of houses. As I say, the demand is always increasing, and we have been looking at where we will get more resources. The lowest resources that in cost is new low temperature geothermal fields. We have 3 to 4 zones here in the capital area that where we are looking for more low temperature resources. We are also looking for high temperature geothermal fields, and we are also looking at waste heat from the industry, such as Gabriel talked about. But it's still too expensive here in Iceland to go into that direction. We still have some geothermal fields that we can go into to get more heat for the future. But we also are using Fluidit. We are developing Fluidit models here in-house. So of course the hydraulic models, but also the water and storm models. And we are looking at how the future development in the municipalities, how they will affect our system, and we use them to prioritize investment in our system. So here we have mapped out, gone and talked to all of the municipalities and mapped out where they are planning to build in the future. These are all the red zones that they have said that they are planning to build and develop in the future. And of course, they also have increasing just in the downtown area here in Reykjavik. So we have a model, hydraulic model of our whole system that you can see here. And then what we do is we map out and connect it to the zones that the municipalities have said they were developing, and said that, okay, the green ones are okay for our system. The yellow are maybe not the best ones, and the red ones we have difficulty to implement the increase in the demand there. And that means that we need to do something for increasing the transmission pipes to be able to give those zones more hot water. And that has helped us quite a lot when we're dealing with politicians, when they have said what their forecast is in developing the municipalities. So we are implementing more sensors, both flow and pressure sensors in all our system. That of course helps developing the models quite a lot. We are also starting to implementing smart meters in our system, and we are have the aim to directly link all our sensors and smart meters to the hydraulic model and get something called digital twin then for our system. And then we can start predicting usage in real time, and of course linking it to weather forecast to see how the system will behave if in the future when we get some cold fronts in the winter time. And that of course helps us quite a lot with providing customers with better data information. We have implemented one digital twin in quite a zone which has quite a clear model boundaries. It's not the most interesting zone. There's nothing happening there. We don't have any development of new houses, but this is a very good zone because we have all the data to develop a digital twin, and we got a lot of help from Fluidit to develop this, and this was a very good project to show the people here how we will implement this digital twin, and we were really happy with this project. That was a little bit about the Icelandic system.
Awesome, Egil. Thank you very much for that presentation, and giving us, I guess, quite a different view and angle from the much more novel, growing and still maturing UK side of things. And I just will hold questions to the very end there, but we can jump over straight to Panu. And Panu, please take the floor. And we can all see your screen there, so that's perfect.
Yep. Thank you, James. So I'll start right away so I try to catch up the schedule a little bit. So good afternoon, everybody. My name is Panu Kauniskallio and I come from Fortum, where I'm responsible for general design and hydraulic modeling of our district heating and cooling systems in Finland. And today I'm going to briefly present you our approach for waste heat utilization from hyperscale data centers in Espoo district heating system. I've divided the presentation into 3 sections, starting with a brief introduction of ourselves as a company, then continuing with the waste heat utilization from our network perspective, and ending with details of the waste heat recovery process. But without any further ado, let's jump into today's topic with the introduction. So, who are we? Long story short, and without looking too much back to the past, we are a Finnish energy utility focusing mainly on producing CO2-free electricity in the Nordics. But in addition to the electricity generation business, we are producing district heating in Finland for over 90% of the citizens in Espoo, Kauniainen and Kirkkonummi area that contains approximately 250,000 inhabitants in total. And when it comes to the key figures of this business, they look like the following. So let me use the pointer a little bit. So the annual heat sales is roughly 2 terawatt hours per year, and the peak power is approximately 900 megawatts. And then we have approximately 900 kilometers of network, which includes 9 pumping stations. And the system also has We have 3 CSP units, 11 heat-only units, and several small-scale producers. And finally, we also have 7,500 consumers. And we also have a district cooling system in Espoo. Then we have some regional heating and cooling solutions, both within and outside Espoo district heating system, as well as some district heating businesses in Poland, but these all are not mentioned here because they are quite irrelevant concerning today's topic. But what is actually extremely relevant to the topic is our Espoo Clean Heat program that is aiming for exiting from coal at 2025 at the latest, as well as having a completely carbon neutral heating production by 2030. And the next illustration will show why. So this illustration shows our journey towards the carbon neutral heating production here in Espoo system. And as we can see here, the journey started already in 2014. And since then, quite a lot have happened. And in future, alongside these electricity-based production units here, these hyperscale data centers will play an extremely significant role as we are trying to reach our CO2 targets. And according to our schedule, which is shown here at the bottom of the illustration, the data center production will start between late 2025 and early 2026 with a relatively small total heat output at first, but this output will gradually ramp up as the time goes on and the data center regions develop. And this illustration in turn shows the key requirements that are needed in order to establish such a waste heat recovery system. And first of all, there are emission-free electricity via transmission system operators grid. And TSO grid is specifically utilized due to the higher 400 kV voltage level, as well as due to lower transmission fees overall. And second, we need to have a big enough plot where the data center is getting built, and the plot needs to undergo an extensive city planning and permitting process before being suitable for data centers. And third, we obviously need data center and the heat pump facility, and these two comprise the actual waste heat utilization process. And fourth, there is a strong data network that is a mandatory piece of infrastructure for data center business. And finally, it is at least preferable that there's big enough heat demand already existing that can swallow as large portion of the total excess heat output as possible. Now, having looked at the introduction to data center waste heat recovery, let's now move on to have a look at the district heating network related aspects. This is our network as it is today. Our existing baseload plants are located here at the southern parts of the system, as well as here quite close to this power plant area. And these almost all of our most significant production units are connected to each other with our transmission network, which contains pipelines with a diameter higher than DN400, so DN500 and so on, the bigger ones. And when we are connecting new data centers, the main goal is that we would like to connect them directly to this existing transmission network. But the problem is that this system has been developed over the past 60 or 70 years, assuming that the base load will always be located here but as it is going to go away from here, it will require some remarkable investments for the piping. And it will look something like that. When we include 2 new baseload plants with Kolabacken data center here and Hepokopi data center here, the pipeline investments are quite remarkable. And we also have to reinforce the existing network here. And these new pipelines will have diameter varying from DN 700 to DN 400. Meanwhile, this blue line showing the reinforced section will have a new dimension of DN 400, and the old one is, or the present one is DN. No, I said it wrong. The existing diameter is DN 400, and the new one will be DN 500. And this is where Fluidit's products become handy, since all these required investments as well as the oncoming changes in basic principles of the operating the system are evaluated and determined with their software. And the total length of new pipelines, so this red line here as well as this one here, is roughly 11 kilometers, and this section to be reinforced is roughly 3 kilometers long. And in addition to these pipeline investments, we are also going to need a new pumping station, which is pumping heat from Kolabacken towards our existing transmission network. And some of you may notice that there's actually a third data center here, but it's way too far away that it could be utilized for supplying heat into our system, or at least that's the present knowledge. Now we had a brief look up at the network impact, so now we can move on and dig a little bit deeper into the production end of the waste heat recovery system before ending the presentation. And this illustration is about the principle of recycling waste heat, showing the key components: data center, heat pumps, electric boiler, and the district heating network, as well as the designed temperature levels on both sides of the system. So the cooling circuit will take 20 degrees Celsius water and return it back to the heat pump facility at 30 degrees. And then the heat pump facility is able to increase the temperature level on the district heating side up to 85 degrees. And whenever the required temperature level is higher than this, then we need to use electric boiler in order to increase the temperature level up to 115 degrees. And when we look at the now figures from energy perspective, so 70% approximately from the total heat output will be from data centers waste heat directly. Meanwhile, rest of the heat is from either electricity used by heat pumps or electric boilers. And these form the total output of 100%, which accounts for approximately 0.8 terawatt hours a year in our case. And finally, we have a little bit more detailed diagram about the process, how things are connected to each other. And the most significant difference between the previous one and this one is that there's actually air-to-water heat pump modules connected to the cooling circuit. And these are quite handy in 2 ways. So first of all, we are able to produce more CO2-free heat, especially during the ramp-up phase of the data center, so between 2026 and whenever the data center region is fully developed. And secondly, if there's some sort of downtime, for example, due to maintenance tasks, then we can still utilize this water-to-water heat pump facility, even though there's no supply of heat from the data center region. And then we also have these electric boilers that can be either used individually parallel to this water-to-water heat pump, or it can be also used in series with the heat pump facility. So in that case, the water would flow from here and go through the electric boilers and reach the desired temperature level that can be up to 115, as described earlier. And given this, the total district heating output can be up to almost 190 megawatts per data center or per heat pump facility. And as I showed earlier, there will be 2 of those. So total output from both of these is almost 400 megawatts. And I think that's everything from my behalf. And since this was the last presentation, I think we can now open the floor for discussion and questions.
We certainly can. Thank you very much, Panu, for your presentation and for all of the 3 speakers that we had today.